Swayam Prabha. Digital India. Educated India.
Hello and welcome. Let's continue with differential geometry of surfaces. A little recap. So last time we had classified points on surfaces with respect to the tangent plane. Let's revisit that discussion. So we had the surface patch, we had a point P, we had a tangent plane passing through that point, we had another point R on the surface patch, we had drawn vector PR and a normal to the tangent plane N at P. We computed this distance D as the projection of PR on N. Let me quickly go through the math and highlight the salient points. So this 2 by 2 matrix here was something we called the second fundamental matrix. It involved the second partial derivative of the parametric equation of the surface patch with respect to one of the parameters u, mixed second partial derivatives of r with respect to two parameters u and v, and the second partial derivative of r with respect to the second parameter v. And also this matrix involved the normal vector to the tangent plane. We had found the equation for D, which is the projection of PR, 2 points on a surface patch, on the normal passing through the point P on the patch, as half L du squared plus 2m du dv plus n dv squared. We figured that the tangent plane intersects the surface at all points where d equals 0, and we had computed the corresponding condition for that. So we had L du squared plus 2m du dv plus n dv squared equals 0, and that gave us the expression for du in terms of dv and the three coefficients L, m and n corresponding to the second fundamental matrix D. So we had du equals minus m plus minus the square root of m squared minus ln over L. We considered 4 cases. The first case corresponded to this discriminant m squared minus ln smaller than 0. In that case, we had no solution. So point P was the only point common between the tangent plane passing through it and the surface patch. We call that point the elliptic or elliptical point. The second case, where the discriminant m squared minus ln equals 0, where L squared plus m squared plus n squared is greater than 0, we have a condition which corresponds to the equation of a line. U minus u0 equals minus of m over L times v minus v0. That implies physically that the tangent plane intersects the surface along a straight line. We call such a point P as a parabolic point. The third case, when the discriminant is greater than 0, In this case, we have two real roots for du. So the tangent plane physically at P intersects the surface along two lines passing through P. We name P in this case as a hyperbolic point. And the fourth case, of course, is when the elements L, M, and N of the second fundamental matrix are all 0, in which case we call P as a flat point. Today we talk about Gaussian and mean curvature surfaces in lecture number 35. But first, let's talk about normal and geodesic curvatures. So we have a surface patch and we have a curve, let's say, laying on the patch. We plot a point P on the curve and we a tangent along this curve at point P. We also sketch a vector normal or perpendicular to this vector T, and we call it N. Now here I would want you to follow the construction rather carefully. Let's sketch another vector and call it N sub C. So N sub C happens to be the unit vector along this direction, and the magnitude of this vector, let's say, is given by kappa. So this vector is kappa times N sub C. I'll tell you what or how NC is related to these two vectors. Let's extend this normal vector N in the opposite direction and name this vector kappa sub N times N. Let's join the two heads of these two vectors and name the resultant vector as kappa sub G times Tg. T sub G is also a unit vector along this direction. The question you would want to ask yourself is, how are these two vectors N sub C and T sub G related to T? N sub C is the first derivative of T with respect to the parametric arc length. So N sub C would be perpendicular to T, and you'll have to be a little observant here. If you realize T sub G is a vector that lies on the plane defined by this vector N and this vector N sub C. Consequently, T sub G will also be perpendicular to T. Let me repeat. The unit tangent here is perpendicular to the unit normal. Since NC is the first derivative of T with respect to the parameter S, which is the arc length parameter, NC is perpendicular to T. So the plane containing N and NC is perpendicular to T. Or let me put it the other way around. Tangent T is perpendicular to the plane containing N and NC. And by construction, TG happens to lie on this plane. So TG will be perpendicular to T. Once you understand this geometric construction, let's proceed with some algebra and nomenclature, of course. K sub n is equal to kappa sub n times n, and we call K sub n as the normal curvature. K sub g is equal to kappa sub g times t sub g, and we call this K sub g as geodesic curvature. K is equal to kappa times nc, which is this vector here. And that is given by the first derivative of the tangent with respect to the arc length parameter, as I mentioned before. And by vector algebra or vector law of addition, Kn, which is this vector, plus Kg, which is this vector here, equals kappa times nc, which is k. Now we know that this normal and this tangent are perpendicular, so n dotted with t is equal to 0. We differentiate this one time with respect to the arc length parameter s. So we have total n over total s dotted with t plus n dotted with total t over total s equals 0. All we have done is we have differentiated this expression with respect to s. Now, since k sub g and n are perpendicular, k sub g is this vector here, and we have constructed this vector so that n and kappa g times tg make a 90-degree angle here. So we'll have k sub g dotted with n as 0. Okay, coming back to this result, dt over ds dotted with n is equal to k sub n plus k sub g, this vector dotted with n. Now if you realize, this vector comes from this relation here. Okay, we expand this result here. So we have k sub n dotted with n plus k sub g dotted with n, and because of the construction, because this angle is 90 degrees, kg dotted with n is 0, so we are left with k sub n dotted with n. We substitute for k sub n as kappa n times n dotted with n, which is equal to kappa n, the scalar. Now dt over ds dotted with n is equal to minus of dn over ds dotted with t. You bring this on the right hand side, and this is equal to minus of dr over ds dotted with dn over ds, simply because the tangent t is defined as the first derivative of r with respect to s. What is r here? R is the parametric equation of this curve. Now this is equal to minus of dr dotted with dn over dr dotted with dr. How did this happen? One has to be careful. It gives you the impression that this dot product is getting transferred to the numerator and denominator, while this is not the case directly. Let me explain this to you on board. So this is how this happens. Let's say we have this curve R as a function of the arc length parameter S. I can also write this thing as R as a function of another parameter U. This curve is lying over a surface patch that we are considering. Now minus of dr over ds dotted with dn over ds. I said that this was equal to minus of dr dotted with dn over dr dotted with dr. How did this happen? Let's find out. So I can write ds as modulus of r dot du, and I can substitute this result here. So I get minus of dr over modulus of r dot du dotted with dn over modulus of r dot du. Since these are scalars, I can club them together. I can write this thing as minus of dr over modulus of r dot squared du dotted with dn over du. This is equal to minus of 1 over, what is r dot squared? This is equal to dr over du dotted with dr over du. Times dr over du dotted with dn over du. So I'll do a little hand waving here. If you notice, this result is a limiting case of limit delta u tends to 0, delta r over delta u dotted with delta n over delta u over delta r, so these are vectors, over delta u dotted with delta r over delta u. The numerators are vectors here, while the denominators are scalars. Maybe I can take the scalars away, and I can write this thing as 1 over delta u square delta r dotted with delta n over 1 over delta u square delta r dotted with delta r. I can cancel these. So I'm left with limit delta u tends to 0, delta r dotted with delta n over delta r dotted with delta r. Under conditions that delta r's and delta n are very small, we can change the notation and we can write this result as dr dotted with dn over dr dotted with dr. There was a negative sign here. This is how probably we get from here to here. What's next? Now what we can do is we can decompose dr and dn along parametric lengths du and dv. So here we are going to be using the information from the curve and try to convert that into the information pertaining to the surface patch on which the curve lies. So dr equals r sub u times du plus r sub v times dv. Likewise, dn equals n sub u times du plus n sub v times dv. You can also think of these results being obtained from the first order Taylor series expansion. Now dr dotted with dn, the numerator in the result that we had seen before, is equal to ru dotted with nu times du squared plus ru dotted with nv plus rv dotted with nu times du dv. Just in case if you have forgotten what the subscripts mean here, r sub u is the partial derivative of r with respect to u, and r sub v is partial derivative of r with respect to v, and the same goes for n sub u and n sub v. We have the final term of dr dotted with dn as plus rv dotted with nv times dv squared. Likewise, the denominator of the previous result, dr dotted with dr, is equal to ru dotted with ru times du squared plus ru dotted with rv plus rv dotted with ru times du dv plus rv dotted with rv times dv squared. In terms of the elements of the first fundamental matrix G, ru dotted with ru is G11 times du squared plus 2 times G12 times du dv. Each of these is G12 plus G22 times dv squared. This is what dr dotted with dr is. Now we can use the fact that both the tangents are u and are v at a point on the surface are perpendicular to the normal to the surface at that point. So we have our u dotted with n is equal to 0, and if we differentiate that with respect to u again, this implies the second partial derivative of r with respect to u dotted with n plus r u dotted with nu equals 0. This implies r u dotted with nu equals negative of r sub uu dotted with n. Now, if you look at this expression here, this corresponds to the first element L of the second fundamental matrix. Likewise, r v dotted with n equals 0 can be differentiated with respect to v to get r vv dotted with n plus r v dotted with nv equals 0. This implies that r v dotted with nv equals minus of r vv dotted with n. And what is this? This is equal to minus n, the fourth element of D, the second fundamental matrix. Let's use this relation again and maybe differentiate this with respect to v. So we'll get the mixed derivative here, r uv dotted with n plus r u dotted with nv equals 0, and this implies that r u dotted with nv equals minus of r uv dotted with n, and this result here is equal to minus of m, and this is the second or the third element of D, the second fundamental matrix. We can likewise differentiate this expression with respect to u to finally get minus of r vu dotted with n equals minus m. Where are we heading? Let's find out. If you notice, we were after computing the expression for the normal curvature, kappa sub n, and this would be equal to L du squared plus 2m du dv plus n dv squared over g11 du squared plus 2g12 du dv plus g22 dv squared. This is equal to L plus 2m times mu plus n times mu squared over g11 plus 2g12 mu plus g22 mu squared. Okay, let's get back to this expression here. Let's go back and try to recap what we had done. So here we had the expression for the normal curvature, kappa sub n, which was equal to minus of dr dotted with dn over dr dotted with dr. We expanded dr in terms of the tangents ru and rv. Also, we did the same for this normal here, dn in terms of n sub u and n sub v. This is a quick recap. We computed dr dotted with dn and dr dotted with dr in terms of the elements of the first fundamental matrix G and the second fundamental matrix D. All we have done is we have substituted for the numerator and denominator for kappa sub n right here. This is dr dotted with dn and this is dr dotted with dr. The minus sign has gotten absorbed in the algebra. What is mu here? Mu is dv over du. All we have done is we have divided the numerator and denominator by du squared respectively. The above equation can of course be written as g11 plus 2g12 times mu plus g22 times mu squared times kappa n. We are transferring this denominator here, and that is equal to L plus 2m mu plus n mu squared. What do we have here? We have a quadratic in mu. That would allow us maybe to compute the optimum value of the normal curvature, kappa n. If kappa n is the objective here, and if you are trying to find an extremum or extrema for kappa n, we'll have to use the first order conditions that correspond to the total of kappa n with respect to mu, and that should be equal to 0 to get a set of stationary points. So if we differentiate this expression with respect to mu, we have g11 plus 2g12 mu plus g22 mu squared times total kappa sub n over total mu plus 2 times g12 plus g22 times mu times kappa n, and that is equal to 2 times m plus n times mu. So this here corresponds to the differentiation of the expression on the left hand side, and this here corresponds to the same for the expression on the right hand side. All we need to do is we need to set d kappa sub n over d mu equals 0. That would give us g12 plus g22 times mu times kappa n equals m plus n times mu. This expression goes off to 0. Therefore, kappa sub n is equal to m plus n mu over g12 plus g22 times mu, and this is equal to L plus 2m times mu plus n times mu squared over g11 plus 2g12 mu plus g22 times mu square. Where did this expression come from? If you notice, this is how kappa n was determined before. This here gave the original expression for kappa n. So I can write this expression as L plus mu plus mu times m plus n mu over G11 plus G12 times mu plus mu times G12 plus G22 times mu. All I have done is I have separated this term here and likewise I have separated this term here, and I have rewritten this addition in the numerator here and correspondingly the addition in the denominator here. We can simplify this to kappa n equals m plus n mu over G12 plus G22 mu, which is equal to L plus m mu over G11 plus G12 mu, which implies that m minus G12 times kappa n plus n minus G22 times kappa n times mu is equal to 0. I would advise you to work and get this expression by hand. We also have L minus G11 times kappa n plus m minus G12 times kappa n times mu equals 0. So this equation here, which are two equations if you think about it, can be rewritten in these forms. In matrix form, I can write these two equations as m minus G12 times kappa n, n minus G22 times kappa n, L minus G11 times kappa n, m minus G12 times kappa n, these four elements form this 2 by 2 matrix, times the column vector containing 1 and mu, and this is equal to 0, column vector. If you want to have a non-trivial solution to these two equations, this matrix has to be singular. In other words, the determinant of this matrix has to be 0. That would give us G11 G22 minus G12 squared times kappa sub n squared minus G11 times n plus G22 times L minus 2 times G12 times m times kappa sub n plus ln minus m squared is equal to 0. We have another quadratic in terms of kappa sub n. So kappa sub n squared minus G11N plus G22L minus 2G12M over G11 G22 minus G12 squared times kappa n plus ln minus m squared over G11 G22 minus G12 squared is equal to 0. This equation is the rewritten form of this one. In short, we have kappa sub n squared minus 2 times capital H times kappa sub n plus capital K equals 0, with H as this coefficient here, G11N plus G22L minus 2G12M over 2 times G11 G22 minus G12 squared, and K as ln minus m squared over G11 G22 minus G12 squared, which is this constant here. So if you notice, the normal curvature kappa n is expressed in terms of the elements pertaining to the first and the second fundamental matrix. To be more specific, we are also talking about the extremum points for kappa sub n. Of course, we know by now how to solve a quadratic equation. Kappa sub n equals h plus minus square root of h squared minus k. So we'll have one extremum kappa n max or k max as h plus square root of h squared minus k, and a minimum kappa sub n min equals kappa min, which is equal to h minus square root of h squared minus k. This coefficient here, h, is called the mean curvature, and k is called the Gaussian curvature. So today we did quite a bit of math. Let me try to solve an example for you on board so that we can absorb the discussions in this lecture. Let's try to determine the Gaussian and mean curvatures for a monkey saddle. The monkey saddle is given by r, a function of two parameters u and v, as u times vector I plus v times vector j plus u cube minus 3 u v squared times vector k. I'll show you later how this looks graphically, but for now let's try to compute the elements of the first and the second fundamental matrices. In ordered form, I can write this thing as u comma v comma u cube minus 3 u v squared. So we have r sub u, which is partial r over partial u. This is equal to 1, 0, 3 u squared minus 3 v squared. We have r sub v equals partial r over partial v. This is equal to 0, 1. This would be 0. We'll have minus 6 u v. We would need the second partial derivatives as well. Let's try to compute them. So r u u equals partial 2 r over partial u squared will be equal to 0, 0. Derivative of this expression with respect to u, this would give us 6 u. Partial r u v equals partial 2 r over partial u partial v, which is equal to, I'll have to differentiate this with respect to v. So I'll have 0, 0, and this is minus of 6v. The mixed second derivative r u v is partial 2 r over partial u partial v. I've already computed that. The second derivative of r with respect to v, r b v equals partial 2 r over partial v squared. This is equal to, we'll have to differentiate this expression here with respect to v. We'll have 0, 0, and minus 6 u. We would also need the expression for the normal. As you would know, this is equal to r u crossed with r v over the absolute value of this numerator, r u crossed with r v. Let's try to determine this cross product first. R u crossed with r v is equal to the determinant of I, j, k r u is this expression here, 1, 0, 3 u squared minus 3 v squared. R v is this expression here, 0, 1 minus of 6 u v. Let's expand this determinant. So we have I times 0 minus this times this, which is minus of 3 u squared minus 3 v squared plus j times this times this minus of this times this. This minus sign goes off. We have 6 u v plus k times this minus this times this. We have 1. So the unit normal n is equal to minus 3u squared minus 3v squared times I plus 6uv times j plus k over square root of 3u squared minus 3v squared the whole square plus 36u squared v squared plus 1. Let me write this denominator as d, and I can simplify d as under root of 9 u4 plus 9 v4 minus 18 u squared v squared. We'll have 36 u squared v squared from here. So this becomes plus 18 u squared v squared plus 1. I'll be needing this side of the board. So what I'll do is I'll transfer this result right over here. So n cap equals 1 over d, where you know what d is, times minus 3u squared minus 3v squared comma 6uv comma 1 in the ordered form. Let's start computing the elements of the first and the second fundamental matrices. G11 equals Ru dotted with Ru, and that is given by 1 plus this squared 3u squared minus 3v squared the whole square. G12 is given by Ru dotted with Rv, which is this dotted with this. So this multiplied by this is 0, this multiplied by this is 0. We are left with minus 6uv times 3u squared minus 3v squared. And G22 equals Rv dotted with Rv, and that is equal to 1 plus 36 u squared v squared. You know what the first fundamental matrix is, given by G11, G12, G12, which is the same as G21, G22. How about the second fundamental matrix? The elements are given by L equals RUU dotted with N. RUU is here, N is here. So what do we have? This dotted with 0 plus this dotted with 0 plus 6u. So we have 6u over d here. Let us not confuse this symbol d with the second fundamental matrix itself. Let me change that symbol let me call D as D sub 1, just to signify that D1 is nothing but the absolute value of this vector. So we have D1 here. The second element M is given as R U V dotted with N. This is equal to minus of 6V over D1. This dotted with 0 plus this dotted with 0 plus this dotted with minus 6V. And the third element N is R V V dotted with N, which is equal to minus 6U over D1. The Gaussian curvature K is given by Ln minus M squared over G11 G22 minus G12 squared. This is equal to 6U over D1 times minus 6U over D1 minus 6V over D1 squared over G11 is 1 plus 3U squared minus 3V squared G22 is 1 plus 36 U squared V squared minus G12 squared, which is 36 U squared V squared times 3 U squared minus 3 V squared, the whole square. The mean curvature H is given by H equals G11 N plus G22 L minus 2G 12 M over 2 G11 G22 minus G12. The square term appears here. You have the expression for G11, G22 and G12 from here. You also know what N, L and M are from here. All you would need to do is substitute for these variables or elements to get the mean curvature. Once you have the Gaussian and mean curvatures, you can compute the minimum and maximum values of kappa n, the normal curvatures. Kappa n max min, as you know, is given by h plus minus under root of h squared minus k. For the example that we had just worked out, This figure here shows the monkey saddle. This shows the maximum principal curvature, kappa sub n, shows the minimum principal curvature, kappa sub n. This is the plot for the Gaussian curvature, and this is the plot for the mean curvature. Why are these curvatures important after all? With the help of these curvatures, we can identify certain classes of surface patches. For example, for developable surfaces, the Gaussian curvature is 0. As you would know, cylindrical and conical surfaces are developable surfaces for which the Gaussian curvature is 0.